In question number 2 of our series, where we learn how to find the inverse transforms of a function, we're asked find y if the Laplace transform of y is equal to s minus 1 over s squared plus 4s plus 20. As you can tell, I've given this a difficulty rating of medium, and this is relative to what we did in question number 1, where we looked at 2 separate examples on how to find the inverse. The first thing that I did in question 1 is I tried to model this function so that it looks like one of the known Laplace transforms in this list. Let's see if we can do the same. We have s minus 1 over what appears to be a quadratic at the bottom. If you look carefully, you'll notice that none of these match what we have here. The only thing that comes close is number 24. Take a look. In number 24, we have what appears to be a quadratic at the bottom and a variable plus a constant a at the top. What can we do to the following equation so that it actually looks like that? I want to make this look like s plus a over, and the denominator is s plus a squared plus b squared. The first thing that I'll try to do is see if I can complete the square for the bottom part. By completing the square, you go from an equation that's in standard form, which is this one, to one that's in vertex form, which is this one. How do we complete the square? Well, the first thing that you have to do is spot your s term, and for us it's 4. You divide that by 2, and you end up with 2. You raise that to the power of 2, and you get 4. So you take your expression, s squared plus 4s plus 20, and you will add 4 and subtract 4. And then you take this positive 4 and place it right there where you have s squared plus 4s plus 4 plus 20 minus 4. You combine these two terms, you end up with positive 16, and this is a perfect square trinomial, which can be written as s plus, you go back to this number, plus 2 to the power of 2, and this can be written as 4 to the power of 2. This expression and this expression look very similar. In fact, we can extract that this number is equal to our a. So we found our a to be 2. However, if I place this 2 into here, I won't get s minus 1. So let's play around with that. We'll have s plus 2 over s plus 2 squared plus 4 squared. Remember, we started with s minus 1. To make this top part into s minus 1, what I'll do is I'll place brackets around s plus 2 and add and subtract 3, because s plus 2 minus 3 is equal to s minus 1, which was the original Laplace transform of y. And if I do that, I can now split this up where I have s plus 2 over s plus 2 squared plus 4 squared minus 3 over the same denominator. This now models the following, and we can look at the list and change it with e to the power of at times cosine bt, where this is my a and this is my b. Let's do that right now. I just finished that one off, and I can use this relationship for this term, where I have e to the power of negative, and my a is 2t times sine. Our b here is 4 again, times t. Keep in mind that our b's are not the same. This is a 3 and this is a 4. So if we pretended that this was equal to 4, we can write down 4 here and make that into a fraction where we have 3 over 4. This 4 and this 4 will cancel out, leaving us with the 3. And this will change. To compensate for this change, I'll write down 3 over 4 as the coefficient. As a final touch, of course, you can factor out e to the power of negative 2t, bracket cosine 4t minus 3 over 4 e to the power of negative 2t times sine 4t. This right here represents the Laplace transform of y, or the function of f of s, our frequency function. And there you have it. That is how to find the inverse transform of a function.